Good morning, everybody. Welcome to the SESAR webinar on exploring the boundaries of ATM on trajectory-based operations. My name is Andreas Hasselberg, and I will guide you through this webinar today. To improve your experience during the webinar, the recommended browser is Chrome or the newest version of Firefox. And if you're connected to VPN, please disconnect from VPN that can limit your bandwidth. Also, make sure that if you have bandwidth problem, nobody else is using your Wi-Fi extensively. We have two presentations today. They are both from exploratory research projects. And to give you a little bit of background information, as you probably know, SESAR has implemented an innovation pipeline, and at the beginning of the innovation pipeline, we have exploratory research. These projects explore new concepts, they integrate new ideas from other domains into ATM, and they prepare the transfer of these new ideas and technologies into our industrial research. I think the title of this webinar fits quite well to these projects. They are indeed exploring the boundaries, and they go beyond and extend these boundaries. Exploratory research is structured in calls. We have launched the first call in 2016, the second call, the third call both in 2018, and the third call recently closed at the end of 2019. In the moment, we are in the process of launching the new call and starting the new projects. Today, we have two presentations out of the ER3 call. These projects recently closed and have now the possibility to give you an overview of their results. We have the projects Adapt and Cotton. They both worked on new ideas to support trajectory-based operations. We have foreseen to have 15 minutes presentation for each of the presentations, and after that, 10 minutes to answer your questions. So, how do we ask questions? On your screen on the right, you have the chat tab, and a lot of you are already using that to exchange some greetings. If you click on questions, you get a second tab that's used for questions towards the presentations. There's another tab called Polls. We will use that to get some feedback from you during the presentation. And if you click there, you already see we have launched two polls to ask for your familiarity with the first topic. So, we will start with the Adapt presentation. This presentation will be given by Tatiana Bolic. We also have Lorenzo Castelli here with us today to support during the Q&A session. So, without further ado, I hand over to Tatiana. Tatiana, can you please come on stage?
Hello. Good morning to all. And let me start sharing the presentation. So I'm very pleased to tell you a little bit more about the results of our project, which was called ADAPT, Advanced Prediction Models for Flexible Trajectory-Based Operation. I have my colleague Lorenzo Castelli with me. We are both working for Università degli Studi di Trieste, and we'll tell you about our project now. So here we will take you through current flight and capacity planning, the ADAPT objectives, models and model testing we did, and the data visualization tool we used to show the results of our project. The project has been performed under the guidance of Università degli Studi di Trieste as a project coordinator, and we had wonderful partners in TU Delft, University of Westminster, Deep Blue, and Università degli Studi di Palermo. So to start, on your poll, you also have the polls tab, and there we have two polls for you. If you could start answering them, that would be great. In today's ATM system, current flight and capacity planning is done mainly by airlines and ANSPs. And airlines, they need to know their schedules at least 6 months ahead before each season starts, to be able to publish their OD pairs, their departure and arrival times. So that's known at least 6 months ahead, and sometimes even longer ahead. However, the trajectory planning by the airlines is quite flexible, where they need to submit their initial flight plan 120 to 3 hours ahead of flight, which gives them enough opportunity to take a lot of uncertainty factors into account, like bad weather, regulations, availability of a certain aircraft or crew, etc., which gives a lot of flexibility for their operations. However, they don't need to consider airspace capacity. They don't even have the information, and the only information on airspace capacity comes in the forms of regulation in today's planning. ANSPs are navigation service providers. They start doing their initial rosters about 12 months ahead, depending on the ANSP. Sometimes it's a bit further away. They have their initial capacity planning, which is then updated along the months. And a lot of times they use historical traffic as a prediction for the traffic on the day of operation. When the day of operation comes, then they get the information on flight plans, and they also know what are the availability of their ATCOs, which sometimes this mismatch of 12 months ahead up to a few hours ahead in some portions of the network brings demand capacity imbalance, which then results in delays. Having that in mind, we thought in the ADAPT to design and test models that would provide information on flight flexibility and saturated portions of airspace, which could then be used to enable strategic collaborative flight planning. Our objective is to enhance predictability while at the same time preserving and quantifying flexibility, while we look at the predictability through earlier, fully shared information on trajectories and airspace capacities. And here we also talk about the airport capacities. And flexibility is expressed as time windows. So what is a time window? The time window is checked for entry in each sector or airport. So what is a time window? Time window is a time interval around the scheduled or assigned departure time or entry time at a certain point. Let's say here it's a sector, even though these are the countries. So you can see within this time interval, which could be 10 minutes, an aircraft can depart either before or after the scheduled time. Then you see that they can be of different sizes. So this one is rather small because the capacity could be that the capacity of this airspace is used up, so there's not a lot of space to maneuver. The smallest time window along the trajectory is assigned to the flight because that is the one that constrains the flight the most. The duration of a time window delineates the degree of flexibility granted to the flight. So here's another representation of a time window. You can see the assigned departure time or sector entry time. And the time window, we had a model that could extend only in the future, or you can have that extends also before the assigned time and after asymmetrically, or it could be done symmetrically. So we did test different versions of the time window, forward, asymmetric, symmetric, and also different durations of the time window. To do that, we have two modeling steps, and we are using optimization models. So in the first step, we assign a trajectory to each scheduled flight. We use a model that we named Strategic Air Traffic Assignment Model, out of which we get trajectories assigned to each flight, scheduled departure times, which means that you also have scheduled entry times in each sector along the trajectory. And these trajectories and times respect the capacity of the network. They minimize flight's operational costs, of course, at the system level, not at each flight. And they guarantee the predictability because we know at each time during the day how much of the load is expected at each sector or airport. The second step is we use a different model on these assigned trajectories and scheduled departure times, where we assign the flexibility. So each trajectory is then assigned the time windows of a certain duration. So we do have these two, as I mentioned, these two models are optimization models, and there is a lot of notation and a lot of different equations. So if you are interested in that, let us know. We'll share our deliverables in the papers we published with you, but we didn't think it would be very useful to do this in this presentation. We did test our models. We created our models and then we tested them on 1 day of real air traffic data that we obtained from Eurocontrol's DDR2. We chose September 1st of 2017 as that was the 5th busiest day of that year, and it was not unduly loaded with different unduly disrupted by either union action or very bad weather across the whole Europe. So in this day, we have about 30,000 flights for each of these flights, we have aircraft type, departure times, trajectory options, because for each of the flights, we have not only one, but few trajectory options so that the models can choose different trajectories so that we can respect capacities. We also have airspace configuration as it was changing throughout the day, and show which sectors were open at which time of the day and what was their capacity as it was on that day. We also use different costs because we are minimizing flight costs. So we have costs on fuel, route charges, cost of crew, cost of I'd say it's different cost of maintenance that we took from Cook and Tanner's report, and they were also part of our consortium. Then what about the results of our models? Well, the models work on this scale because we managed to get these models to come to the optimal solution. What is the good news is also they are acceptably fast for strategic pre-tactical time horizon. So the first model, the first results on an old computer, we had it reached the results in about 800 seconds, and I think now we can diminish that with the new computer, and we're not even talking about the very high level performing computer. And the second model is also working in about 300 to 500 seconds. So it's acceptably fast for strategic pre-tactical time horizon. So what can we see from the results? So these are the results we get from the models, which are not very, you will agree with me that we're not very useful for the people in operations because you really have to go and sift through that to figure out what they mean. So with that, we thought to create data visualization tool, which was done by great help from our Deep Blue partner. And before showing you the data visualization tool, let me introduce the key concepts. We have constrained flight. So flight is constrained if the duration assigned to it has a time window that is shorter than the maximum allowed duration of 15 minutes. So if a flight has time windows of 14 minutes, then it's constrained. Then we have saturated or critical sector hour, which means that the capacity of that sector during that hour has been reached because we use the capacity as the number of entries within an hour. Then we have criticality index, which measures the degree of criticality of a sector hour as the total additional number of the time periods that all flights constrained by the same sector hour would have if it had sufficient capacity. So if a sector has sufficient capacity, all the flights passing through that sector during that hour have time windows of 15 minutes. If the sector becomes constrained, then if the capacity gets filled up, then the time windows of the flights passing through become lower than 15 minutes. That in mind, let me show you now a video that shows you our data visualization tool. The ADAPT objectives are to improve predictability and quantify and preserve flexibility, and also to serve in collaborative decision-making process of strategic flight planning. So what can be done with the results of our models? We show this by demonstrating the data visualization tool that shows just mentioned capacity utilization of airspace network elements, criticality index of sectors and ACC, and critical flights. First, we have model parameters button where we can choose a different version of a model. Here we are showing the asymmetric model with 15-minute time windows. Then we have view settings button where we can choose a flight level at which to see the results and the time of day, and also if we want to check use capacity or spare capacity. At the right hand side we have a legend that shows the values of criticality index and use capacity and how the colors change across the according to values. And then on the left-hand side, we have different visualization by sectors or by ACC of fears. We can also pull out the ACC hourly maps and performance indicators. At the sector view, if we click on a sector, we have the sector name and the capacity of that sector in that time of day, and also the capacity utilization. The reddish sectors going to white are the ones that have completely used up capacity and they constrain certain flights. If we click on them, we can see trajectories of the flights that are being constrained, and if we click on a trajectory of a flight, we can see the what are also the flight details. So origin, destination, time of departure, aircraft type, then we have what is the maximum negative shift, maximum positive shift, and sum, which is this total duration of the time window. If we click on a sector that is more white, we can see that that sector constrains many more trajectories. What can be done with this data? An airline can choose to check which are the flights that are critical for that airline, and then they can choose either to reroute or maybe be very careful on how they perform that particular flight. If we go to the ACC and FEAR visualization, we can the NSPs can see what are the criticality indexes of that particular configurations, and maybe they can choose a configuration that better serves the foreseen traffic. We can also see how these things change across the time of day. And here, this is a little bit slow. I see this is a different thing, and if we go at in the evening, you can see that there are no problems in the evening. We also have performance indicators tab where we can see distribution of criticality index of sectors across the day. We can see that we have about 2,900 critical sector hours a day out of about 30,000. We have average criticality index of sectors by hour plot. We have a number of constrained flights, which is about 13,000 out of about 30,000, which was the busiest day, one of the busiest days in the year. We have number of critical sectors, airports per hour of the day, where airports are yellow and sectors are orange. We can see that there's about 47% of utilized capacity on the network of the day, so we have a lot of spare capacity in the network. We have number of constrained flights per hour in the plot, and we also have average percent of sector capacity utilization by hour. Okay, let me share with you again. So we've seen that the video that shows you a little bit the how we went through the data visualization tool. We can also get the hourly map for the ACCs. This takes a little bit longer to load because it does a lot of calculations on it. So we just show you the figure here. So you can see how the criticality English change across the NSPs in Europe along the day. So with that, that was most we had. Well, to be able to do for the next steps, we were thinking that you know, a bit more of a testing on how this would work, and also getting more in touch with the airlines and ANSPs, and showing how this could actually work in the daily life. Because I mean, the models work, the information is there, but this would completely change the way of how airline dispatchers work, and also what ANSPs are allowing for the flight planning at the time. So that would need more research to see if that would be acceptable or not. That's all for me. Thank you very much for now. So Andreas.
Yeah, thank you, Tatiana. So now we have time for a few questions, but I think first you had another poll.
Oh, yes, we have another poll in which, Remy, if you can get the last Oh yeah, the last poll, yeah, so it's there. So what would you like to learn more about the work done in ADAPT? If you could fill out that poll, that would greatly help us. And if you want any other detailed information from us, just get in touch and we'll be happy to share. And for the video, I've seen that there is that sound was low. We will, I think, Triona already probably posted the link to the video, so it will. I'll also put it in the chat box so you can check it in your own time if you're interested. And here is also the link on this slide. You have the link to the ADAPT visualization tool, and you can play with it on your own. Okay.
Okay, yes. Now everybody has the opportunity to write some questions. We will try to answer them. And I see that already during the presentation, Lorenzo and also Tanya, when she had the time, answered the first questions. So what's still there to be answered? Lorenzo, do you want to come on stage?
Okay, there is a question from Sonar that Lorenzo, you're muted, Lorenzo. Do you want to answer now in to Sonar?
Yes.
Instead of writing to them, you could just provide your answer here.
You know, the aim. I mean, first of all, thank you for raising the point that you also developed this mathematical model. That would be great to share our views. And also, I would like to answer to some of the question before. So you have seen that there is this visualization tool, and this is freely available online, and you have the link here. So, and you can see. Then, as Tanya said, the visualization tool is fed by our MILP, integer linear programming model. So if you want to share, we are now writing a paper, but there is a deliverable which are available. Again, it's free on the project website, so you can have an idea there on what to do. And then about the future of our project. So what we show here is mostly the deterministic part. One of our members, the consortium member in Delft, they also developed a model with a stochastic view, and the deliverable is available there, and also with some more sophisticated way of addressing congestion in Palermo, and again the deliverable are available. So the aim, of course, the future aim of our project, of course, would be to try to see to what extent this can be useful for the stakeholders. This is a very low. This is exploratory research, so it's very low TRL. So it's I think 1. So but the next step now would be try to include and try to give the idea of strategically. How we can try to predict in a strategic way, which would be the traffic, and also to answer to Matthew about the functional. Maybe Tanya can say also a word on that. For us, the sector was more or less geographic sectors. Of course, we took into account all the configuration, which are open, which are closed. So it's very careful work on that. So we replied, I think, in a very pretty precise way what happened on that day, on the 1st of September 2017. But I would say it's more on the geographical side. Tanya.
Yeah, we use the geographic side, and there is again to get the data that fed this model. That was a work of art, because well, the trajectories are rather easy, but then you also have to choose which trajectory. Is it initial? Is it the actual? Is it the regulated one? We took the initial because it was the strategic. We looked at the strategic, so we wanted to have the earliest information possible, and the initial flight plan is the earliest information available to us, at least. And then for the sectors and capacity, we have also in the DDR data there is a sector declared capacity, but then sometimes it's done through this construct that's called traffic volume, which takes into account different flows and this and that. We didn't take that into account, but we, I mean, in terms of flows, we did take that into account in increasing the capacity of those sectors where it was obvious that having those flows pass through, you could see that the entry count, for example, you would have capacity of 10, but you would see that the entry count on any day was 30, then we would put the capacity of 30. So we did a lot of data preparation, data cleaning before the model, before running the models.
Okay. I can give a short answer, maybe also if you have time, Andreas, to Raimund.
We still have time.
Okay, to Raimund. It's not Tanya, it's Lorenzo answering, but I think it would be fine as well. So would there be any first come, first serve logic for the congested areas? Yes, it did, but it's this is more on a tactical side, okay? So as it is today, according to the CASA algorithm, our model, as Tanya just said, is more strategic. So we are still in the position that we can decide whether to anticipate or slightly delay what is the assigned time of depart or the scheduled time of departure, right? So when the first come and first serve, it's a rule which is applied, I would say, just a few hours before the takeoff time. So it's a kind of different perspective on the time horizon we are addressing.
And there is a question now from Mehta. It says, is the strategic phase you refer the ATFCM strategic phase? Which time frame is it? I don't know if it's exactly ATFCM strategic phase, but we're talking about 6 months to a couple of weeks before the flight. I mean, again, that's another thing. That's the next step of our research to see where it would be useful to put this in, not to create too much additional work on different stakeholders. We've shown that the models work, they could be used, the information is there, but where exactly to put it in the workflow and where it would be most useful, that's another thing to research.
Okay, are there any more questions? Please let us know.
No, it doesn't seem to.
No.
There's also a question.
Uncertainty on weather. Yes. We have still time for this one.
Okay, Juan, do you somehow take into account uncertainty? No, we don't, because we're talking about the strategic thing, and that's not, nobody's really, I mean, maybe airlines are taking that into account through the buffers and the flight block time, but we are just taking the information on trajectories from the historical data.
Yeah,
we're not taking that into account.
In this model, but in the project, we did, I mean, Delft did the...
that was for the assessment.
Yeah, for the validation assessment, and then you can see in the deliverables that is in the website, and this was made by our colleague in Delft, where they validated our the strategic model that we in Trieste developed. Then there is also they did take into account the weather uncertainty, and the deliverables are available on the website.
Yeah, and there was a Mehtap also said that one of the challenges we face is availability of data that early in time, which is true, and that's another reason why we think that there was something to be further explored. Once upon a time, there were repetitive flight plans that were, they still exist, but they're not used as much. And it's, again, as I say, that's something to research further.
Okay, still a few questions. Still a bit of time to answer one of the questions that just arrived. Which one do you want to pick?
There is a question from Olaf that says, your strategic planning is based on the airway system, isn't it? What will happen when trajectory-based ops will be implemented? Well, our strategic planning is based on the trajectory data we have, which in that period in 2017, they were based on the airway system, but our models can take whichever one the model says input data take the times of departure, times of entry in sectors. So for us, it doesn't really matter which type of trajectory, which type of system is used to build a trajectory. We just need to know when the trajectory pierces certain volumes of airspace. So it can be applied whenever, whichever system.
Okay, thank you both very much. I would like to come to the second presentation now, and maybe you could answer the 2 or 3 open questions on the chat during the next presentation.
Okay.
We will.
Good, thank you.
Thank you all very much.
Thank you very much.
So the second presentation will be given by the Cotton, or will be about the Cotton project, will be given by Eva Pontero. And also she brought some support with her. We have done a thing here to support during the question and answer session. So Eva, would you like to come on stage?
Yes.
Hey, good morning.
Hello, everybody. Good morning. I'm gonna share my presentation. Yeah, here it is. Okay. I'm pleased to be here. I'm going to present Cotton project, which is also an exploratory research project. With me is my colleague Danlin Sen. We both work for CRIDA, the Research and Innovation Center of NAIRE. And we led this project, which is about capacity management and complexity metrics for supporting it. Well,
we already have launched 2 polls.
Yeah.
These are to ask you about your familiarity with the topics of the project. So please go to the poll tabs and reply.
Yeah, the thing is, I'm not sure I'm able to see the result of the polls. Yeah, I see we are quite a lot familiar with DAC and FCA. That's good because Cotton project is based on the assessment of these 2 concepts. These 2 concepts, DAC and FCA, persecutes to better balance capacity, to be more adapted to the expected demand, and to avoid or to minimize the deviation of the aerospace users' planned trajectories. DAC, Dynamic Aerospace Configuration, is based on the design of the aerospace using non-predefined aerospace structures, adding much more flexibility at the aerospace design process. Flight-centric ATC is a concept which envisages that several controllers might be working in the same sector, managing the whole trajectory of the aircraft in a flight-centric area. As you can imagine, there are some challenges to be faced by these 2 concepts in order to allow their flexibility. For example, the capacity thresholds nowadays are linked to the operational sectors, the operational procedures, and the historical data we have about these sectors. Complexity assessment is usually based as well on the sector knowledge and the expertise of the operating procedures in the operational sectors. So there is a need to rework the complexity assessment and the workload assessment methods in these environments, DAC and FCA. Uncertainty. Uncertainty is also an issue, as you can imagine. It presents a risk to have problems of stability in the planning of the aerospace if we do not manage the uncertainty currently in the planning of DCB processes in these concepts. And finally, there is a need to assess how these two concepts should coexist and how we should plan the deployment of DAC or FCA to achieve the best network performance and the best capacity performance of the ATM. This is the problems addressed by Cotton. How do you think that the Cotton approach to solve these problems? Well, firstly, what we did in Cotton is to assess complexity metrics available in the ATM research domain, and we stick to develop complexity methods, probabilistic complexity methods that firstly to integrate uncertainty, and secondly to account for the particularities, singularities of DAC and FCA concepts. We address the complexity measurements taking into account the assessment of the workload of implied by the mode of operations of dynamic aerospace configuration and flight-centric, and also to try to develop methods to evaluate capacity in this mode of operations. And finally, we develop how to use these complexity metrics in the demand and capacity balancing processes of DAC and FCA. What are the Cotton results? Okay, Cotton has mainly three kinds of results. First, the development of three complexity metrics, solution space, which is developed by TU Delft. It's a metric which evaluates the available space to apply air traffic control maneuvers. Geometric metric, which is developed by ENAC. It is based on the assessment of purely traffic trajectory factors and evaluates traffic complexity. And finally, cognitive complexity metric, which is developed by CRIDA and is an abstraction of the traffic factors, which has an implication on the cognitive processing of the air traffic controller. We have reviewed each and every process in the demand and capacity balancing in DAC and FCA, and we have assessed how these three complexity metrics should be used to better support the design and the configuration of the aerospace. And we have worked as well on the integration of DAC and FCA. Today, I will present just one example of the application of Cotton in DAC, how to use cognitive complexity to support two specific use cases, which are the identification of the sector configuration, DAC sector configuration, and the evaluation of remaining hotspots. We have activated a new pool in order to collect the challenges you see we can expect from DAC in these use cases. So what do you think are the key open issues to ease DAC feasibility? Well, what are the improvements that that concept will provide to the DCB? What are the expected improvements demonstrated by Cotton experiments? In terms of cost efficiency, Cotton solution, the use of cognitive complexity, probabilistic cognitive complexity, will provide a more stable airspace configuration, will allow higher flexibility to the ANSPs to design the aerospace, and also according to the fast time simulations and data analysis we carried out in the project, we found out that it is possible to reduce the number of sectors and also to achieve a more balanced workload. In terms of capacity, we observed a better detection rates of overloads. We achieve better mitigation of the hotspots, and in consequence, we think we can reduce capacity buffers if we apply the use of probabilistic cognitive complexity to support the aerospace configuration design. In terms of safety, although we were in exploratory research and we apply validation techniques in this maturity phase, mainly data analysis and fast time simulations, initially we assess the number of conflicts expected, and we did find that there is not expected more conflicts than in the reference scenario. Just a brief introduction of what cognitive complexity is. When an air traffic controller is managing the aerospace, it has to make an abstraction of the air traffic being managed, the structures, and there are several factors that will increase the workload of the air traffic controller. Cognitive complexity takes into account the interaction, quantifies the interactions between flows, the potential conflicts, the number of evolving flights. It considers the number of flights in and out of standard flows or standard flights, and also considers the sector shapes as the main factors in the load of cognitive complexity. We developed a tool whose main entrance input is demand uncertainty. We use probabilistic demand, flight plans also from the DDR database, and we compute this demand to obtain the quantification of these complexity factors and to obtain probabilistic complexity, probabilistic cognitive complexity. Just to show you an example of application of the use of cognitive complexity. This is the use case we applied in the fast time simulations. Firstly, there is a need to develop the strategy of the ANSP to be applied. For example, if they decide to minimize the average cognitive complexity and cognitive complexity derived from the sector shape, and also minimize the number of sectors, or for example, another strategy could prioritize the balance of the cognitive complexity. Then, with cognitive complexity and applying the cost function strategy, the automation could provide the demand and capacity balancing user, for example, the FMP, could provide the sector configurations that are most optimal according to the defined criteria. In this example, you see, for example, 3 aerospace configurations for a given area. The first 2 contains 3 sectors, and the third contains 4 sectors. The user could evaluate as well the cognitive complexity for the proposed configurations. For example, in this example, the red line is the threshold of the cognitive complexity, which is evaluating in a 0 to 5 scale, and the threshold is set at 3.5, 70% of cognitive complexity. And we represent the percentile 30% and 10%. It means, for example, in this sector, CGITS, The automation foresees 7 minutes hotspot duration with a 10% of probability. We could monitor the evolution of the complexity evaluation according to the evolution of the traffic demand. And if previously we assess the prediction of complexity 3 hours before, here we are assessing the prediction of complexity 30 minutes before. And here you see that the proposals are different. Now, the best configuration contains 4 sectors. Anyway, what-if function should be available to assess the previously proposed sector configurations. And finally, just to analyze the validation results, we checked in Cotton validations the prediction of the cognitive complexity against the actual cognitive complexity and also against the occupancies that took place in the traffic samples analyzed. This is more or less the overview of Cotton solution proposed for DAC. I want to make emphasis that we not only address DAC solution, we also address, for example, the flight traffic allocation, the flights allocations to flight-centric controllers in FCA concept, and also the design of the FCA area. Here, there is activated a new pool, which is about your interest in Cotton project. Just my last slide to summarize the next steps in the development of Cotton solutions. There is a need to refine the NSP's strategies to ensure the stability of the configuration plan. Also, cost functions could be improved, including machine learning or artificial intelligence techniques, and also to better incorporate underload detection, because Cotton solution is currently very focused on overload, and we found out in the validation that it's also very important to take into account underloads. And there is a need to test further validate these solutions in real-time simulations with human-in-the-loop activities in order to assess the human performance component. Just for your information, we are working as well in SESAR Industrial Research, Dynamic Aerospace Configuration, Solution 44, and also Solutions 45 and 733, which are the projects where these concepts are being developed, and it is expected that some of the outputs of the projects are included there. That's all from my side. Just to say that the Cotton Consortium is composed by these partners, CRIDA, ENAC, Eurocontrol, DLR, TU Delft, and Polytechnic University. This is the web page where you can find all the public deliverables of the project.
Okay, thank you very much. It's time for questions again. Some questions were already answered during the presentation, but we have a few minutes for more, so please don't hesitate to ask questions. Danlin, do you also want to come on stage?
Yes. Hello, everyone.
Hi. Hi.
Answering the questions.
So, which did you already answer? Which are still there? There is a question from Soner. Is there an upper limit of sector shrink after all?
Yeah. Let me see. So, about the, is there any upper limit of sectoring after all? Because after reaching a point, satisfied sectoring does not mean anymore. How do you determine this point? Okay. So this is about maybe the point to determine whether to use DAC and the area to use FCA, because indeed, if you can split the sector in a very small size, and then you reach a limit, and when you cannot provide any more capacity. And so one of the exercises of Cotton is the integration of DAC and FCA. And the main result of this exercise is that we see that for FCA we can put it in the upper sectors, because FCA is more by now is validated for upper sectors, is working better. And then in the lower sectors we can put DAC, and depending on the demand and capacity balancing, we will switch from one to another in the time evolution. So yes, we have a upper limit, but in Cotton research results, since this is a exploratory research, we haven't researched in that deep of the number of a quantity result, but we can see that we have acceptance because one of the exercises is indeed to combine two operation environments. So another question is
there are two questions.
Is Cotton tool available for research purpose? Yes, I think in the last slide, Eva has mentioned that Cotton tool is proposed to be used, or Cotton results is proposed to be used in the different industrial research projects of SESAR in the 44, 45 about DAC, and for the 73 for FCA. So we have made the tool available for them. Yeah.
New question has arrived.
Will you make the FCA relevant results traffic allocation also available? Yes, indeed. We have launched the last poll to see where are the interests you have on the project, and maybe we can go further in the topics. So yes, for the FCA we also have relevant results, and you can see them already in the Cotton deliverables, which are purely on the website. But yes, we can give further details. How weather and unusual situations are managed. As a first attempt for the uncertainty, we only considered to integrate the time uncertainty of the traffic to be considered and introduced in the complexity metrics. Further, in the next steps, we will. The idea of Cotton is to manage and to address the other uncertainty sources, and one of the main uncertainty sources will be the weather, actually. But in this step, we did not assess these abnormal conditions. Do you take into account consideration systems like CDM, AMAN, demand?
CDM, yes, because we consider the definition of the DCB processes. AMAN and demand, no, because we were focused on en route capacity,
yes.
en route sectors.
Okay, any more questions? We'll wait a while. No, maybe not. So in any case, I think you can contact the speakers later on. They provided the details, and Before you all leave, I just wanted to remind you about some upcoming webinars. We'll have another webinar on exploring the boundaries of ATM next week, where 3 exploratory research 3 projects will give an overview of their results. These are the projects Gateman, Evo ATM, and Domino. They worked on ATM architecture and on CNS. And then in 2 weeks' time, we will have 2 webinars about nurturing young talent. One will feature winners of the SESAR Young Scientist Award, and the other the winners of last year's Digital Sky Challenge. So no further questions have arrived in the meantime. Then I would like to close this for today. I would like to thank you all for attending, and I would like to thank the speakers for presenting the project and for answering your questions. So I hope to see you next time. Goodbye.